All right, so we've talked before about numbers. We talked about numbers, one-dimensional, two-dimensional, three-dimensional concepts. Higher dimensions are possible as well. So if we talk about the number 7, we can think about where that number is relative to, say, some number line, some arbitrary location for 0, and some scale. So if we need a direction, we need to know where the positive direction and where the negative direction. So typically we would do it like this, but we can make that line turn any direction we like and have positive or negative in any direction we like, put the 0 wherever we need it. But if we said, for instance, that the scale was here, and that was 7, then we know where 7 is relative to that 0 on that line. It's not actually where 7 is, but in that context, right? That's where 7 is. And so a number has with it this idea of location. Also, if we think of it in 2 dimensions, if we, again, put our positive x and our positive y in that way, whichever direction we like, we know what to do with it. And we think about this point right here. Let's say that point is 3, 3. There's a location associated with it, but that location, again, is relative to the origin, the scale, and which direction is positive x and which direction is positive y. But once we settle those things, we have that kind of location in mind. Well, numbers like 7, mathematicians tend to call these, instead of just calling them numbers, in the context of what we're talking about, they'll call these scalars. And so a scalar just is a number, but we'll see why that word gets used. So what we're going to talk about is the idea of a vector instead of just a number. So vectors have associated with them 2 components, a magnitude, or a length, and a direction. So there's an algebraic approach that involves putting coordinates in place, but there's the geometric approach, and that's what we care mostly about for our purposes, but we will consider these together, geometry and algebra, as appropriate. But there's a magnitude and a direction. So we have some length associated with it and a direction associated with it. So if we say something like drive north at 60 miles per hour, what do we have? We have a direction and we have a magnitude in terms, in this case, of how fast we're going. But both of these are part of what it means to be a vector. You have a magnitude and a direction. What does drive north at 60 miles per hour not have associated with it? Sorry? Height. Okay, so no height associated with it. What else does it not have associated with it? It doesn't have a location associated with that, right? Drive north at 60 miles per hour, you could do that in a lot of different places. But if we were drawing this on a map, we might draw an arrow pointing north and have the length represent 60 miles per hour. So a longer arrow would mean going faster, a shorter arrow means going slower. But what could happen? We could put that arrow over here, or over there, or down here, wherever we wanted to put that arrow, and it would all correspond to driving north at 60 miles per hour. So there's a lot of other features that aren't associated with that. But in terms of the main thing that's missing in terms of a vector is an actual location. This vector here is the same as that vector, is the same as that vector, because the main pieces that matter, direction and magnitude. All right, so with vectors, vectors are like other things that we learn about. What do we want to be able to do? we want to be able to, first of all, we understand what they are. There's a direction, there's a magnitude, and then just like other things that we've learned about, then we want to learn how to add them and subtract, and what can you do with these things. All right, so if we have a vector, say vector A. Now what's going to happen in describing a vector, when I write it on the board, or, well, just on the board, I will write a lowercase letter with an arrow over top to indicate that it's a vector, that it has direction. When we type it, say, on an assignment, especially in an assignment in Blackboard or something, I'll use a bold-faced character, just lowercase letters, individual letters. In Python, what would we probably do? We would give it a more descriptive name, right? Don't just call the vector A, but we would have some descriptive name of describing what this vector represents. If on the board I write A like this, this means a scalar. With the arrow means a vector. Later we will have a situation where we will use a capital letter when we're writing. Again, that will be for a matrix. We'll deal with that when we get there. But again, when we name things in Python, we will give more descriptive names of what's going on. It's better that way. All right, so we have this vector A. And what does it mean? It means that if you start from the location of the tail and you follow that direction for that length, you end up at the head of the vector. So we're going to draw these usually with an arrow directed segment like this. But the idea is it doesn't matter where you start, this vector corresponds to the idea of movement. You were here at one place and now you are someplace else. All right, so what would happen if I had vector A and then I had, say, vector B? So the idea here is if we start at the tail of A, at some starting point, and then we move in the way described by vector A, and then from there we move in the way described by vector B, what have we done overall? We started here and we ended there. So we have this vector that corresponds to A plus B. Now again, remember the vectors don't have location, but the idea is if you did start somewhere and you did the motion described by vector A, and then you did the motion described by vector B, this is the meaning of A plus B. Right? You started there and you ended there. Now, how you got there might be different, right? If we actually followed A and actually followed B, we went around this way in terms of a path. Whereas this is a straight line path, but the idea isn't, the vector is not describing how you got there, it's describing where you ended up. So if you did A and followed it by B, you started here and you ended there. And that's what the vector tells. All right, so you kind of think of this maybe in terms of a force. If there's a force being applied to something, it's going to start moving in one direction. And if a different force comes along, it changes its direction. Where does it end up? And if these are being applied at the same time, something in that direction and something in that direction, the object might follow along that path, that actual path, that straight line path to get to where it was going. All right, so this is the geometric meaning of A plus B. One motion followed by another motion. Where do you end up from the beginning to the very end? Again, remember, the vector could be somewhere else. The vector B doesn't have a location, so we can't really talk about its location. And so often what we do when we have a vector, because it's easier to think about, sometimes we will imagine that the tail is at the origin. even if it's talking about a point somewhere else, often we imagine it with a tail at the origin. So here's vector A. And so when we want to describe vector A algebraically, we might describe the pieces in terms of the motion that's involved. So what motion is involved in getting from one point to the head of the vector? I don't know, maybe this is you move to the right 3 and you move up 3. I don't know. So maybe that's the description, right? So wherever you start, you move to the right 3 and up 3, and that then is describing the other end of the vector. So when we write this, we often write it like this. Now, the author of the textbook sometimes puts commas in between when they're writing it out like this. When we enter these, when we write a vector class, we're going to enter it vector with parentheses, and we'll list the components. Sometimes you see a vector written like this instead. So this is what's called a row vector. Geometrically, it doesn't matter, but algebraically it does. So there are certain things that we'll see later that sometimes we want things written as a row, sometimes we want things written as a column. Sometimes it is an actual difference in terms of what's going to happen. They'll take on different meanings, different applications, depending on whether we're talking about a row or a column. All right, so what happens, and then other times they're just interchangeable, so it just depends on what we're trying to do. But what happens here, the idea is a vector geometrically just means we're moving from some point to some other point, but it's the relationship, it's how far we moved and which direction we moved that matters. And otherwise, algebraically, we apply or attach coordinates to things. Now, what happens if we have a third component? So this was the x and the y. What if we had a third component? Then we would just move that far in the third direction, right? So if we're x, y, z, we're moving however far we need in each of those ways. Now, if this had been, say, 3, 4 instead of just 3, 3, does it matter if we move the x direction first and then the y direction, or the y first and then the x? Well, we're going to end up at the same place, right? If you moved up 4 and over 3, it's the same as having moved over 3 and up 4. We just have to remember that this is the left-right and this is the up-down in that particular drawing. There are some things that we can do, though, where it does matter, the order of things. Rotations, for instance, especially if we have rotations and then movement, or movement and then rotation, it really matters. There can be a difference. If you imagine standing up and facing me, or actually if you did that, stand up and face me, and let's move away from things that are around so you have enough room to do some moving. What happens if you're facing me, directly facing the front of the room, let's say. If you take a step forward and then rotate to your left 90 degrees, and think where you are. Now go back to the original place that you were, in the same way, just go back to where you started, facing this direction again. Now let's rotate 90 degrees to your left and take a step forward. Are you in the same place? No, right? There's a big difference between that motion and that rotation, or the rotation then the motion. But if you faced forward, again, face this direction, now take one step forward and one step to your right. Now go back to where you were, take a step to the right and then a step forward, and what happens? You're in the same place, right? So those motions, without the rotation, you're perfectly fine. It doesn't matter which order, just as long as you remember which one is left and right and which one is, up and back or whatever. Okay, you can go ahead and sit down. But what's the idea? That rotation being involved can make a big difference. So later, when we're dealing with the rotation, which is a big part of the reason that we are doing the math that we do, that rotation, we have to be really, really careful. The order you do that, what's going to happen? are you really ending where you want to, or are you ending up somewhere else? Even if you're in the right spot, if you're pointing the wrong direction, then that matters. So we'll talk about orientation and some different aspects as we go forward. All right, so we have vector A drawn here. And let's suppose that we do the same thing with vector B, but we draw it, again, with its tail at the origin. And this was vector B. So let's say vector B was, I don't know, looks kind of horizontal. Let's just say it's 4, 0. Right? You go over 4 in the x direction from wherever you were. You go over 4 in the x direction, and you don't go up or down any in that case. All right, so what does A plus B look like in this case? Well, again, from the geometric thing, we could have put B up there. And so A plus B should point in that direction. So this is A plus B. So another way to think of A plus B, rather than putting tail, head, and then the tail here, is we could imagine a parallelogram with the tails of A and B together, and then this is B, just in a different location, which location doesn't matter, and this is A in a different location. And so what happens? A plus B is going to point from one end of the parallelogram, one corner, to the opposite corner, right? And so A plus B would point in that direction. Well, what would it be algebraically? How far over do we go? Well, A moves us a distance of 3 in that direction, and B moves us 4 more. So total, we've moved 7. And then A moves us up 3, and B moves us up none. And so A plus B looks like this algebraically, right? So what do? Adding component by component. All right, so we can have two vectors in a vector class and add them together component by component. Again, what happens, it's not necessarily, well, it's not at all that the vectors are touching in any particular way because vectors don't have location, but we can imagine that movement followed by the other movement in this way, or we can imagine drawing these in this way. So what happens, there's kind of a connection between, or a relationship between the points in the plane and a vector that points from the origin to a particular point. But again, that vector, vector A, wow, okay, let's not move vector A, let's move vector B. Vector B could be here, there, right? Its location isn't part of what it is, just how much motion is involved. Okay, so that's adding. What happens? We have a vector. Now we know geometrically what they are. We have some idea algebraically what they are. And we know how to add two vectors together. So what might we do instead of adding? We might think about subtracting a vector from another vector. So we could think of this as being, again, subtraction is always thought of as adding the opposite of something. Well, what would the opposite of a vector be? What would that mean? Yeah, if a vector pointed that way, then the opposite is going to be just the same exact vector pointing in the exact opposite direction. Any vector, the opposite, just change the direction. And so that's the geometric meaning of the opposite, is just point the other way. And so what would happen geometrically in this case? We have A here. This would be negative B, right? The opposite of B, pointing the opposite direction. So if we did the geometric approach, put B up here, A minus b looks like that. Well, where does this fit into this picture? A minus b is right there. Right? A minus b points from the head of B to the head of A. Does that make sense? Well, let's see what's going on here. This says geometrically that we've gone B first and then we do this other thing. So let's see what happens. If we do the motion associated with B and then we do the motion associated with this other thing, what happens? We did a motion associated with B, did a motion associated with A. So that would bring us over B, and bring us up here, and then bring us back here. Right? Which corresponds to the motion associated with A. Does that make sense? And so that's the reason this vector is A minus B, because it's what you have to add to B in order to get A. All right? So A minus B is going to point toward A, but on the arrow end, right, on the head end of both of these vectors. What about B minus A? So B minus A, if we think about A minus B and flip those, what happens? That's negative A, that's B. And so what does B minus A do? B minus A points toward B, right? The opposite direction. So it's exactly the same vector lengthwise, but it points opposite direction. All right, so what happens? Adding is what you expect, one thing followed by the other. Subtraction is, again, what you expect, one thing, but it's followed by the other in its opposite direction, whatever opposite means in that case. All right, so algebraically, what would happen? A was 3, 3, and B was 4, 0. So what is A minus B? Negative 1, 3. Does that correspond to what we've done here? We're going to the left and up. So that corresponds, negative 1, 3. What is B minus A? One, negative 3. And from there, what did we do? We went to the right one and down 3. So that corresponds. Right? So the algebra and the geometry match, but the idea, again, is really the geometric approach. What kind of motion do we end up with? If you did this followed by that, what's the result? Or again, often we have both of these forces being applied at the same time, and so the thing is moving in that actual direction by the combination of those two. So we know what a vector is algebraically and geometrically, and we know how to add and subtract them. All right, so what comes next? Well, when we learned about numbers, we added, subtracted, and we started to multiply. So let's see what's going to happen here. We have a scalar multiplication. And a scalar multiplication, again, is a number, but scalar multiplication means a number multiplied times a vector. So for instance, we had our vector A. We might multiply 2 times that. Mathematically, when we write this and when the author writes it in the text, they just write the numbers side by side. when we're doing this in a Python program, we're going to have to do this kind of thing, right? 2 times the vector, which means what will we have to do? We will have to define what that means. So what method will we use to define what that means? We'll have to use these 2 that we saw in the fraction class earlier. This one, my wireless mic quit working, so I have to use the wired one, which barely works as well. Keep pulling things off. So this has the vector on the right, so we're going to have to use that. If we wrote it this way, we'll create that method as well. All right. So again, though, when we're writing it, we just tend to write it the typical kind of mathy way. What do you think 2a means? Well, 2a, we can think of that, since that's an integer, we can think of it as a plus a, which means what? Do a and then do it again. So where will we end up? The total motion will be 6 units in both directions. What if we had done, say, a third of a? Yeah, then we've done just move 1 in the x direction and 1 in the y direction. Okay, so scalar multiplication will do what? It will keep the direction the same and just change the magnitude, change how far you go in one direction or the other. Well, actually, it'll change how far you go in all the directions, right? So if you had an x and a y, if you had a third, a fourth, if you had 10 dimensions, again, we don't know what that means geometrically, but the idea is still the same. Go this far in that direction and this far in the other direction and keep going. And if you multiply by a third, then you just go a third as far in each one of those directions as you're building. So this is what scalar multiplication does. Keeps the direction of the vector changing possibly its length. Right, the magnitude. We don't have a vector times a vector scenario. We do have certain kinds of products that we can do. There's something called a dot product. A dot product that we'll see later, that you do take 2 vectors and you do a kind of multiplication, but it's not, you get a number, you get a scalar at the end of that. And then there's another kind of multiplication that only works for 3-dimensional vectors called a cross product. And we'll see it later as well. But you put 2 vectors together and you get a third vector, but they have to be 3-dimensional, and there's a very specific meaning that it has. So it's not a generic, a general kind of vector multiplication. So we don't have a general vector multiplication like this. We have very specific cases. The dot product that we'll talk about works in any dimension. The cross product only works in 3 dimensions and has a very specific 3-dimensional meaning. So when we talk about multiplication, we're talking about scalar multiplication. And all we're doing is changing the length of something. All right, so what happens then? The components themselves tell you the direction. If you say go over this far and up or down this far, then that's telling you the direction you're going, even though it's not telling you the exact angle of the direction. It's still telling us which direction to go. So sometimes we will not care about the actual angle. And if we don't care about the actual angle, we can save a lot of resources in terms of, say, a program that we're writing, by not calculating the actual angle, not using the math.sine or math.cosine and so on, just using the vectors. The vectors, we'll see, hold a lot of angular information in the vector. So if we just care about getting the right direction, we don't actually necessarily have to calculate what that direction is. But other times, we do need to calculate what that direction is. And so sometimes we'll have to still use those trig functions. But a lot of times, we're going to be able to avoid using the trig functions and still get the same result at the end. So the trig stuff is hidden away inside the vectors. But sometimes we're just stuck. We have to do the calculation. We have to get the angle to make something happen the way we want it to happen. But the vectors have in them so far the idea of direction. What is the negative then? It's multiplying by -1, right? So what would happen if you did -2 times a vector? -2 times a vector will change its direction and make it longer, right? -1/2 times a vector will change its direction and make it shorter. All right, so how do we calculate the magnitude of a vector? Well, it turns out there are lots of ways to describe the length of a vector. There are different ways that we'll use in different contexts. The basic way we think of, we had that vector A that came out here to the point 3, 3. And I'm writing these as row vectors. A lot of times we will write things as row vectors. Usually in mathematics and physics applications, we tend to need them written as column vectors in the ways that those are used. And so sometimes if you are looking something up, you're trying to solve a problem, you're looking something up, if something is written in row vectors or written in column vectors, you have to make some changes. So it's not just, oh, just turn it. You have to make some other modifications as well. We'll talk about what some of those are. Again, a little later when we get far enough in to see where it actually matters. Right now, it wouldn't matter. Right now, we could be writing them either way. All right, so how do we calculate magnitude? You think about this, that really we are thinking about if you've gone from one point to another point. So what do we have? Because we don't really need the axes. We've said, what have we done? We went over 3 and up 3. So how far did we go? Well, we have a right triangle here that says we went over 3 and up 3. So can we calculate how long this is? Yeah, we can use the Pythagorean theorem. And we get what's called Euclidean distance. Or, well, we'll give a couple of other names in just a second. So how long is this? Right, so first thing would be the square root of 3 squared plus 3 squared, which is square root of 18, which is, as you said, 3 times the square root of 2, which we can calculate that, but that's the exact value, right? We can get an approximate value for that. And that's one way of describing magnitude of a vector, right? Just a regular distance. So this is a two-dimensional vector and calculating distance in that way. This is sometimes, instead of saying magnitude or length, often we'll use the word norm. And this is what is called the 2 norm of a vector. Right? Regular Euclidean distance, the distance formula that you're used to, is the 2 norm of a vector. And we'll talk about what other norms are. Change the number here, and we'll talk about meanings for those in just a couple of minutes. All right, so the 2 norm of a vector is use the Pythagorean theorem if you have this two-dimensional vector here. All right, and so what if the values had been negative? What would we have changed here? Well, you just put the value in parentheses, right? Actually, you can think of it, if it had been -3, say, on one of these, we could think of absolute values But when you're squaring, it wouldn't matter. But really, that's what we're thinking. We're thinking about not the direction. We think about just the length of a side. It doesn't matter which direction that side is pointing. So really, we said 3 squared and 3 squared. Really, we were thinking of the absolute value of that, even though it wouldn't have changed anything in that particular case, because it's the length of a side that matters. So no matter which direction this vector was pointing, as long as it was distances of 3, the overall 2 norm, or the magnitude in that context, would have been 3 times the square root of 2. All right, so let's think about a 3-dimensional version of that. We're in this room, and let's think about calculating the distance from the corner back there at the floor to the corner up here at the ceiling. So let's see if we can figure out how far it is from the back corner at the bottom to the front corner at the top. We could decide, if we wanted, that this, well, it's a 3-dimensional system, right? So we can have an x, a y, and a z. So let's say that looking down at the floor, this is the corner that we're talking about, and I'm standing here. So we could say that, let's say this is the x direction. Just choose that, right? We can just choose that as the x direction, the positive x. And let's say this direction is positive y. So what could we do? We could calculate how far it is from the back corner, back there, to the corner over here. And then we could calculate the distance across the front of the room. And from there, we could calculate that distance. Well, what does that distance correspond to? What in the room does it correspond to? The floor, right? It's the back corner to the front corner, but on the floor. We can calculate that. What would that be? I'm going to call this, I don't know, let's call it D. Actually, probably a bad choice. Just call it A. So what would A be? The square root of whatever the x value was squared plus whatever the y value is squared. Again, assuming that this is actually a right triangle and the walls are square and all that. So that would be the length on the floor, but that's not what we want at all, is it? We want the length from the corners, right, the corner at the floor to the corner at the ceiling. So what could we have done instead of doing anything like this, which doesn't give us the answer we want at all? What if we had stretched a string? What would happen if we tried to stretch a string and measure that? We'd probably get some sag in the string or something, right? And it wouldn't be quite right. So we didn't have our laser scanner from the other conversation we had a while back, right? So we can't do that. Well, so what happens? We can get the length on the floor. Again, assuming that we can get pretty good measurements of the length of the walls. Well, then what would happen? What if we made a new triangle where that is the length on the floor and this is the height of the wall? So now we have a triangle that we're imagining sitting up in the room. What is this? This is the length from the corner at the back of the room, at the floor, to the corner at the front of the room at the ceiling. Does that make sense? Well, how long is this? This is the length of the dotted line, right? That's that part. This is A, that distance on the floor. Well, how tall is the room? That far. It's that tall, right? Whatever the Z component was. So what is our overall distance here? It's going to be the square root of this thing squared plus the height squared. Well, what happens when you square a square root? It's just x squared plus y squared plus z squared. Make sense? And so what happens? This distance is the same as it would have been, at least in terms of the components. This was the x squared plus y squared, and then the square root of everything. This is x, y squared, each one of them. What if this had been a four-dimensional vector? If this had been a four-dimensional vector, four-dimensional vectors are usually written with the fourth component as w, because x and y were already started, and so that gave us this part, but then the w. If you go beyond 4 dimensions, we tend to do something like, if the vector was v, we tend to use like v1, v2, v3, v4, v5, something like that. That's the mathy approach.
When do you need that many?
Well, so we have already mentioned that there's things that we can describe in terms of vectors that aren't geometric, but if we were going to describe a whole bunch of information, say, about this room, we could talk about the temperature, we could talk about the location. So just a location of the room could already have 3 variables. The temperature could be a fourth component, the light level, the humidity, some measure of the sound level. There's a lot of other factors. And then it turns out that the methods that we're developing, I mean, for graphics purposes, we never need more than 4. We do need 4 sometimes. But we could have, on a character, we could describe a character and all of its features in different, and it turns out that we can then use the techniques that are developed for graphics purposes in completely different ways, even though it's not a geometric vector, but the techniques still carry over. And so we'll see a little bit of that later, of some situations where you have a lot more dimensions. It's not geometric, but the things, we mentioned cross product, well, not cross product, dot product. We'll mention some other, we'll do some other calculations, and those calculations can still tell us meaningful things. Not graphically, but at least not directly in terms of, a 3D kind of graphics thing. But you could attach extra components. Think about the function that we use to create a rectangle. The function we use to create a rectangle in Pygame. You have a surface, you have a color, you have an upper left-hand corner, you have a length and a width. So already we have at least 6 components to that. The color has 3 components itself, so we might have even more components, right? So that is a kind of higher dimensional version of this. All right, again, so we can talk about length, even though what does that really mean in 5 dimensions or something? Usually, again, the maths and physics folks start counting as 1 as the first index. We can shift everything over, which we have to do in programming versions. But the idea is still we would number them after there's more than 4. We don't keep going in other directions. All right, so what happens? This distance idea, or again, the 2 norm, is a way of calculating a length, and it's a length that is associated with what we typically think of as the length of something. But it's, again, a very specific length. In general, we talk about a p-norm. So we have a vector, let's say vector v, whatever it happens to be. We can talk about the length of that vector. And we use this kind of notation to describe the length of it when we're writing. It mimics the idea of absolute value. So when we think about absolute value of -7, what are we thinking about? Here's 0, say over here is -7. Absolute value of -7 is the distance from 0 of the thing we're talking about. And so since the same kind of idea is going on we're thinking of the length of the vector, we use 2 bars just to emphasize that it's a vector. Except when we're writing it, we're going to use things like, we'll write a function or something called norm. So maybe we write it as a method, and so we'd have v.norm. Or if we write it as a function, we'd do norm of v. And so we would actually say the name instead of using notation or symbols like that. But what happens with the p norm? The idea is, we'll just do this with 2 dimensions for right now. The same idea carries over. We would do, say if v were 2-dimensional, we would do absolute value of x to the p power, so x is the first component, plus absolute value of y to the p power, and then we raise all of that to the 1 over p power. So the 2 norm, what do we do? Square each component, add them together, and then what does the 1/2 power mean? 1/2 power is the square root, right? So for the 2 norm, and if we write this symbol without a number, it means the 2 norm, right? It's like square root. If you write a square root and you don't put anything in there, it means the 2. If you put something in there, then we're changing it. So the 2 norm would mean square the components and then raise it all to the 1/2 power, or in other words, take the square root. All right, so what happens? Sometimes when we're dealing, especially with like the 2 norm, sometimes we will want to do calculations that don't involve square roots, because square roots are a little more time consuming than other things. You get into round off errors and some other problems that can happen. Floating point kinds of things start to get involved. So often, and we'll see this later, we'll do calculations that involve the square of the actual length. So we'll leave off the square root part. So we'll do all of our calculations and only do a square root if we absolutely have to. So there are times when we can avoid taking square roots. And that'll make things a little bit better overall. We're dealing just with integers. Things will be a little bit faster and less likelihood for floating point errors. But sometimes we, again, can't help that, and we have to do the calculation. We have to do the square root. So we'll talk about that at some different points, finding the magnitude squared rather than the magnitude. And we don't want to just find the magnitude and then square it, because we've already taken a square root along the way. We'll do it without the square root part. So we'll see that a little bit later. All right, so the 2 norm is the one that we're most comfortable with. If we had a 3-dimensional vector, again, you just add the 3rd component. A 10th dimensional vector, you just add all 10 of them. And the same thing with a p norm. If there were more pieces, it's the same exact thing. Each term individually, absolute value to that power, then to the 1 over p. All right, so let's think about the 1 norm. What would the 1 norm of a vector look like? The 1 norm of a vector is going to take the absolute value of the x, then raise it to what power? To the 1st power. So it's just the absolute value of x, right? No change. And then the absolute value of y. And then that answer is going to raise it to the 1 over 1 power, which is just the 1st power. So what do we have? The 1 norm looks like this. Absolute value of x plus the absolute value of y. And that's how we're measuring distance. So what does that correspond to? Let's think. Let's say we were going from here. Let's not go there. Let's go up to here. We're going from here to there. The 1 norm says, how far is that? Well, how far over are we, if we had a vector like this, how far over did we have to go? We had to go a distance of 2 in the x and then 3 in the y. So the distance, the length of this would say 2 plus 3, which would give it a length of 5. Is there ever a time when we would measure distance like that? So let's think about driving in a city. If I want to go from here to there, how far is it? Well, we might say it's 5 blocks because we have to go over 2 blocks and up 3 blocks. If there are one-way streets involved, it might even be further than that because you might have to go past it and come back or something, right, in order to get there on the one-way streets. But we would say 5 blocks, and what this one norm does is measures if you have to stay on the grid. Right? You have to get from here to here, staying on the grid. What could we do? We may move straight over and straight up, or we may work our way over like this. But what have we still done? We've still gone 5 blocks for that distance. So the one norm is sometimes called a taxicab distance or a taxicab norm. It's called a taxicab metric. That's another word that gets used for it. Sometimes it's called a Manhattan distance because it's like driving on a city street, on city streets, where you have to stay on the street. You can't just decide arbitrarily, okay, I'm going to cut through this block because there are buildings there or whatever, right? And so the one norm corresponds to this kind of distance, which at times is the right way to measure distance. If you have to stay on the grid, that's how you measure distance. And so if we have to do that, then instead of this being our distance, this would be an appropriate, reasonable distance. All right, so let's say that we have a vector I think A was 3, 3 before, but let's change it. Let's say we have a vector 2, negative 3. All right, so we're just looking at two-dimensional vectors right now. What I would like for you to do is to write a function we're going to call norm that will take an x and a y value and then the p value and return the appropriate value for that norm. Right? So we take an x and a y and a p, and we want it to return the p norm of a vector with those two components.